definition, people would say coordination number is number of ligands that are attached to metal center. Because when you have ML, you say coordination number is 1. When you have ML2, you say coordination number is 2. When you have ML3, you say coordination number is 3. When it is ML4, you say coordination number is 4. When it is ML5, you say coordination number is 5. When it is ML6, you say coordination number is 6. Which would have been correct? Only that the problem is some ligands could be, let's say, trifles. What is the ligand is trifles? And we are knowing trifles has 3 donor atoms. I mean, trifles has 3 phosphorus atoms to donate. So we'll not be able to follow this again. Because by that time, if the 3 of them are bonded to the metal, are we still going to say that the coordination number is still 1? No, to change. So when you are defining coordination number, you say coordination number is the number of donor atoms in a ligand that is donating to the metal center, or that is coordinated to the metal center. It is the number of donor atoms in a ligand that is donating to the metal center. It is the number of donor atoms in a ligand that is donating to the metal center. So it's the number of donor atoms in the ligand that is donating to the metal center. And then we have factors that affect coordination number. Factors affecting coordination number. Factors affecting coordination number. One of those factors is size of the metal atom. We also have size of the ligand. We also have oxidation number or oxidation state of the metal center. I like to also add this one, steric interaction. Steric interaction. Steric interaction. So we have size of the metal atom, size of the ligand. Let's first of all look at the size of the metal atom. Let's look at how does the size of the metal atom affect it. How does the size of the metal atom affect whether we have a high coordination number or a low coordination number? What we're trying to look at is, if the size of the metal is small, will it accommodate more ligand or less ligand? That's what we're trying to look at. Well, we don't know yet now. We'll look at it and find out why. Now, when we're talking about size of the metal atom, we're basically talking about the atomic radius of a metal. Now, let's go back a bit to secondary school days. Let's just go back a bit. Now, let's look at Mn, manganese. Manganese is 25. Are you with me? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. The reason why I put this 2 out here because it's 4s2 3D, 5. So 2 has to be outside. 4s is the outside. Okay, now let's look at this. Now, for you to know how, when we talk about atomic size, they told us that atomic size increases across the period. Meaning, as you are putting electrons, the size of the radius of the atom will be increasing. Why? Because it's accommodating more electrons. And let me show you another thing. When electrons are inside this place, electrons, like we said earlier, they repel each other naturally. I mean, they are always repelling. Now, imagine that you put 2 magnets in the same place. Imagine there are 2 magnets here now. They are repelling each other, which means that they are likely to stay apart. Now, the fact that they are repelling each other so much and they are staying apart means the size of where they are has increased. Are you seeing that? Now, the more they repel, the more there's an increase in the size that they are. So it's just like that for these two. So the more electrons that are there and they are repelling each other, the more the radius that they will create for their self. Are you seeing that? So that's why they mean by large atomic radius. Now let's look at something. If we say we have Mn7 plus, or let's say we have Mn2 plus, let's look at 2 of them. 7 plus means it should lose 7 electrons, while 2 plus means it should only lose 2 electrons. Now let's look at 7 plus first, or let me look at 2 plus. 2 plus means lose 2 electrons. It will always lose from the outer one before the inner one. So let's say it loses this one. Are you seeing that? It will not lose so much. So the atomic radius will still be what? Will still be big to some extent. It will still be big now. So because it's still big, it means that it has the capacity to accommodate more. So the ligands that it will take in will be more. Are you seeing that? That's for this one now. It will take in more ligands. Why? Because the atomic radius is still wide. So it cannot accommodate more ligands into itself. So basically, I'm trying to tell you now that large atomic size, or let's say large metal size, will accommodate more ligands, leading to what? To high coordination number. Because accommodating more ligands means there will be an increase in the coordination number. Is that not it? The coordination number will increase. But if we look at 7 plus, for example, 7 plus means to lose 7. I've lost 2 before. So now that's another 2. 4 has gone. Another 2. 6 has gone. Then 1. Now, look at it again. Look at the number of ligands, the number of electrons has reduced. So now the repulsion will also what? Reduce. So the size will also what? Reduce. So because the size has reduced now, they cannot take in as much ligand as when the size was bigger. I see that. So small metal size will accommodate what? Less ligands, leading to what? Low coordination number. Look at the note you need to jot down. I'm explaining the factor now. As the explanation to the factors. We'll be taking note of all these things. All these are information that you would use when we are going into every part of the course. I don't know who is messaging you, but you should wait. Size of the ligand. Yeah, let's look at size of the ligand. Now, first of all, think about it with me. If we had a bulky ligand, let's look at it together. Let's say we had CO and we had PPH3. And this PPH3, remember, PPH3 looks like this. Let me draw it here. This is PPHD. And this is CO. And we want to coordinate them to RU. Which one would you put more? Let's say you have to put 6. Which one can you comfortably put 6 of it in this place without any trouble? CO or this one? The one that you can comfortably put 6 of. Which one would you put? This one now. You can easily put CO like this. There will be enough space. Abi? To occupy. But imagine you want to put 6 of this for this guy. Do you think it's possible? It will be very, very compressed. It will be jam-packed. For example now, you put P here. That's the point now here. That there's no where to put this one now. So what I'm saying in essence is bulky group will lead towards low coordination number. When you have a bulky group, that is the large size of the metal of the ligand, will support towards low coordination number. So you can put it there as explanation. Bulky group or bulky ligand will favor low coordination number, while smaller ligands will favor high coordination number. So that is that. Then I don't think I need to now still explain this too, because I just did. Let me show you. This steric interaction now. Steric basically is saying when you have bulky group, there will be some sort of repulsion between this guy and this guy, which is the reason why you cannot put a lot of it here. Are you seeing it? Because of steric hindrance. That is why we cannot put plenty of the bulky group here, because of steric hindrance. So that already explains the steric interaction we are talking about here. Because when there's a lot of steric interaction, you reduce the amount of ligands that you can coordinate with the metal center. Hence, it will still lead to low coordination number. Then this oxidation state of the metal is when I was explaining size of the metal. That I said when you have Mn7 plus and when you have Mn2 plus, which one will take in more ligand? The Mn2 plus. Why? Because it will have a larger metal size and will accommodate more ligand. Why this one will have a smaller metal size and will accommodate less ligand. So that also has already explained the oxidation state. That is that. So let's go to coordination number of 2. Let's look at coordination number of 2. Let's look at coordination number of 2. Okay, let's look at coordination number of 2. For coordination number of 2, Usually, okay, let's say this has an SP hybridization. Has an SP hybridization with a bond angle of 180 degree, and its geometry is linear. Its geometry is linear. Geometry is linear. I told you now it is SP hybridized. Bond angle is 180 and the geometry is linear. It is usually favored by D0 or D10 metal ion. It is favored by what? D0 or D10 metal ion. It is favored by D0 or D10 metal ion. That is one. Then it is also favored by bulky ligands. It is also favored by bulky ligands. Yes, it's favored by bulky ligands because bulky ligands will always give rise to low coordination number. So it is favored by bulky ligands. That's that. That's mostly it for coordination number of 2. So we go to coordination number of 3. Coordination number of 3. It is sp2 hybridized with a bond angle of the bond angle of 120 degree, and the geometry is square planar. Okay, I think I should draw linear for you. Linear looks like this, so that you know. This is linear, just like this. The bond angle is 180, angle on a straight line. Then square planar on the other hand is like this. So this is square planar. Bond angle is 120, 120. So it's like that. So that you know. For square planar, it is also favored by D10 configuration. D10 configuration. It's also favored by D10 configuration. Favored by D10 configuration. And also favored by bulky ligands. Quite similar, only that this one is sp2 hybridized, the other one is sp hybridized. It's favored by bulky ligands and D10 configuration. Metals with D10 configuration. Any English I want to use there. Also have coordination number of 4. This is where there is work. Coordination number of 4. Here we can have 2 possible geometries. The coordination number of 4, we can have 2 possible geometries. 2 possible geometries. We can have the square planar can have the square planar with the DSP2 hybridization, bond angle of 90 degrees. Bond angle of 90 degrees, usually found amongst metals with D8 configuration. Usually found among metals with what? D8 configuration. And then the other possible geometry is tetrahedra. The other possible geometry is tetrahedra. Tetrahedra with sp3 hybridization, bond angle of 109.5 degrees, usually found among divalent ions. By divalent ions, I mean the Zn2 plus, Cd2 plus, Cu2 plus, Ag2 plus. Usually found among the divalent ions with a D10 configuration. Okay, no, Cu plus. It's A2 plus now. With a D10 configuration. Yes, the D10 configuration. Also, D0 and D5 favors this geometry. So D0 and D5 also favors tetrahedra. Yes, D0 and D5 also favors tetrahedra. But what we will now quickly look at is how the d orbital splits for tetrahedra and for square planar. We'll quickly look at the splitting of the d orbital for tetrahedra and square planar. The splitting of d orbital for tetrahedra and square planar. So let's quickly look at that. Have you written this? Yeah. Let's quickly look at the splitting of the d orbital for tetrahedra and square planar. Have you written it now?
Yes.
So let's look at it. The splitting of d orbital for, let's start with tetrahedra first. Splitting of d orbital for tetrahedra. So that way we can understand what they mean by what it favors. Say it favors D0 and D10 and whatever favors tetrahedra. See it now. So first things first, look at the d orbitals first of all. Before we start splitting them, let's look at the structures of the shapes of the d orbitals in space. I need your knowledge here. Please. It's getting serious now. Since I'm playing, we're getting serious now. This is where you ask questions when you are confused. You keep quiet and you carry that question and go everywhere. So how many diopters do we have? It's not 5.
Yes.
We usually have 5 diopters, and that's why we do like this, two box like this, round like this. 1, 2, 3, 4, 5. So we usually have 5 diopters. To us, we see it as just they are in paper like this. But this is actually how they are arranged in space. So this is their arrangement. Now if you look carefully, you realize that 3 have this thing that looks like a ball like this. It's called lobes. Lobes. So 3 have their lobes between axes, right? So as you can see now, this one has lobe between x and y axis. This one has lobe between y and z axis. This one has lobe between x and z axis. But these other 2, they are what? Along the axis. So this one has its lobe along z axis. This one has its lobe along y and x axis. So these ones are what? Between the axis. Why these ones are where? Along the axis. So let's be smart now. I believe we are smart. Now, when matter is in its free state, I'm just going to use here. This is an energy diagram. When matter is in its free state, what will happen? Nothing, right? When matter is exactly. In its free state, it means that nothing will happen. It means all 5 d orbitals will be on the same energy level. Are you seeing that?
Yes.
When matter is in its free state, all the 5d orbital, that is the xy, the xz, the yz, the x squared to y squared, the z squared will be on the same energy level and are termed degenerate. When something is on the same energy level, we call it degenerate. So the xy, the xz, the yz, the x squared to y squared, and the z squared, they are the same energy level and they are termed degenerates. Abi? Now let's now look at something. This is a metal. And we said metals and ligands, they share an electrostatic interaction, right? An electrostatic relationship. Meaning, if this metal notice that ligands are coming, what will happen? We begin to repel. Look at it here. Let's say there's a magnet here now. Eh? You have not put another magnet here yet. You're just bringing it close. You know that you start reacting. Exactly. So when this metal notice that there's an incoming ligand coming my way, it does not even know where the ligand is coming from yet, but there's just incoming ligand coming its way. What will happen is all these d orbitals will begin to repel each other. And that repulsion causes an increase in energy. Although there will still be the same energy level, but the reason in energy. So xy, the x, the yz, the x squared to y squared, and the z squared. they rise in energy to a place that we call spherical environment. Now the reason why we call it spherical environment is because that place there's a cloud of electron around the metal center. Because obviously the metal is called, the ligand is coming. So the metal knows that there's something around me. So it's a place of high electron density. So we'll put it like this. When the incoming ligands approaches the metal center, the d orbitals will experience repulsion. Will experience a repulsive interaction to the ligand and will cause them to rise in energy to a point of high electron density. Called the spherical environment. So they rise in energy to a point of high electron density known as the spheric environment or the spherical environment. Now let's have a look at something. Now when the ligand has now been coordinated, meaning we are now in a tetrahedral field, have you? You know tetrahedral is 109.5. So I cannot really say this thing is standing like this. I mean, because it's 109.5. All the angles 109.5. So it has to be slant in a way. So there's a ligand here. There's a ligand here. There's a ligand here. There's a ligand here. And there's a ligand here. Now if you look very well, this is going to be our z-axis. I mean, that's a straight, I'm putting a straight line now, that's my z-axis. But it's not on the axis. This ligand, is this ligand on the axis? No. This is going to be my x-axis, and this is going to be my y. So this is z, this is y, this is x, z, y, x. The ligands now, are they along the axis or between the axis? They are between the axis, I mean. So if the ligands are between the axis, which of these d orbitals will be experiencing a greater repulsion? If, as you just said that the ligands are between the axis now, if I'm going to put the ligands in the metal, obviously they will stay in one of these d orbitals. Which of the d orbitals will experience a greater repulsion? Which of the d orbitals? Is it the one that is between the axis that will experience a greater repulsion, or the one that is along the axis? Why? Now, the one between the axis will experience a greater repulsion because the ligands are also between the axis. So it's more like you are putting a lobe of electron in the same place that the ligand is. Ligand has electron. That one too has electron. So they will what? They will repel more. I see that. So these three will experience a greater repulsion, forcing them to do what? To rise in energy. That's because why? They are also in the same direction as the ligand. I see it. They are in the direction as the ligand. They are between the axis. The ligand is also between the axis. So they are in the same direction as the ligand. So because they are in the same direction as the ligand, they will experience a greater repulsion, causing them to rise in energy. So we call this the xy, the xz, the yz. Why these other two that are not experiencing any form of repulsion the way these ones are experiencing will do what? Will fall in energy. That's the x squared, the y squared, and the z squared. Which will now cause the d orbital to split into two sets that we now call the T2g and the Eg. So this is the splitting of d orbital for tetrahedra. And the energy difference between here to here is what we call the delta T, crystal field splitting energy for tetrahedron. So we have entered here now. So let's write down the last note now. So we'll say in a tetrahedral field, that's in this field now, the orbitals, the ligands, are between the x, y, and z axis. Therefore, the d orbitals that are between the axes, which are heavily concentrated in the ligand direction, will experience greater repulsion, causing them to rise in energy above the spherical environment. I have to indicate the one between the axes as this one. Put it here. The xy, the xz, and the yz. So please put it in this place. The d orbitals that are between the axes, you now put 3 of them. You start the notes from that place, so
Yes.
when matter is in its free state, start it from there. While the d orbital that are along the axis, which are least concentrated in the ligand direction, will fall in energy below the spherical environment. Causing the d orbitals to split into 2 sets.